Okay, this is a video on factoring polynomials. And we'll start on the whiteboard here, and then we'll look at some things on the document camera. And finally, in Excel. The reason I'm making a video on this topic is that it comes up all the time in the Facebook help groups. 2 or 3 times a week, somebody posts a question, how do I factor this polynomial? And it always gets answered by somebody, but the answers are less than ideal, to say the least sometimes. Usually people figure out one root, do a bunch of division, and figure out another root, and they don't explain very much, and they don't use the tools that we have available over here. Or they use them like the first one implicitly. So we actually have as many as 5 tools to help us do this, and we can do this with very minimal or even 0 division of polynomials. We don't really need to do that in a lot of cases. So the first thing we have is the order of the polynomial. That's the 3 up here. Okay, that's the highest power of x. That tells me how many roots I have, how many factors I have. So in this one I'm going to have 3, and the rest of them I have 4. So I start out knowing how many factors I'm looking for. That doesn't get mentioned a lot. It's often implicit, but it's an important piece of information. So we're looking for 3 things up here. Now the next thing we can use is Descartes' rule of signs. And this is really handy for eliminating some of the trial and error later in the next steps. So the rule of signs says that for the number of sign changes between the terms tells you how many positive roots you have. So here we have no change of sign. Everything is positive. And we have 3 roots. So that means that all 3 roots should be positive, with a possible exception in that. And this works for all roots, whether they're rational. We're going to talk today about rational roots. There sometimes are irrational roots, and there's sometimes complex roots. We're not going to try to determine what those are, although we may encounter them in 1 or 2 of these. And Descartes' rule works in general. So this is going to have up to 3 positive rational roots. Up to, because it may have imaginary roots. There may be a root of the form a plus bi. And anytime there's an a plus bi, there needs to be an a minus bi. And these are not rational roots. So the second possibility here is that I have 1 positive root and 2 imaginary roots. There is another corollary to this, which you don't really need to use, but if I put in minus x for x, and I cube it, I get a minus sign. If I square minus x, I don't get a minus sign. Here I get a minus sign. Now I count the sign changes, and I have 1 change, 2 changes, 3 changes. And this was for minus x. So that tells me I have 3 negative roots, 3 positive roots for negative x. So that's just a corollary, but it didn't really tell me anything here, did it? Here I have no change, no change, change, no change. I have 1 change. So I'm going to have 1 positive root. And how many roots do I have altogether? Well, I have 4 roots altogether. So I have 3 minus, or I have 1 minus and 2 imaginary. I'm going to have, here I have no sign changes and 4 roots, so I could have 4 positive roots. I could have 2 positive roots and 2 imaginary roots up here. Or I could have 0 rational roots, and all 4 could be imaginary. And the same is true here. There's no sign change here. And down here, what's different here is I have a leading coefficient. And that'll make a difference later on. But for now, we still use Descartes' rule. We have 1, 2, 3 sign changes. We have 3 positive roots and 1 negative root. Or 1 positive and 2 imaginary. So in this case, we know all of our rational roots are positive. This means we can eliminate trying anything negative. So we just cut our effort in half by using Descartes' rule. Otherwise, you're going to have twice as many things to try in the next step, which is the rational roots theorem. We're going to work on this one next, on the document scanner, and we can do the rest of them the same way, but at that point we'll use Excel. Excel gives you a powerful way of checking every potential rational root. Once you've identified the rational roots, you can just test them by putting them back into the polynomial to begin with, rather than having to divide. And people also just don't seem to know this theorem and make use of this either. So let's take a look at the first one. These are actually just variations that were created based on this one in order to illustrate some different cases. So we'll go to the document scanner. I'll flip back to this as needed if we need this for reference. We've used 2 of our 5 tools. We know how many roots we have, and we know how many are potentially positive or negative, given that there may be imaginary pairs in there. Okay, so let's go on to the document scanner. Okay, so here we are at the desk with the document camera, and we're going to go to work with these tools that we talked about. We had 5 tools. We have to order the polynomial to know how many roots we're looking for. We have Descartes' rule, which we discussed on the whiteboard. Now we're going to use the rational roots theorem and the remainder theorem, and ultimately make our work easier with Excel. And we're going to look for actual roots of polynomials, roots and factors. So what we're trying to do here is apply these tools and use a methodology to find the roots and factors. Each of these tools is a math topic of its own. You can go on YouTube and find all kinds of videos teaching you about each of these on their own, and they'll demonstrate how to use them on their own. But what I'm just not seeing in the help groups is the ability to put all these tools together into a methodology to actually solve a problem using whatever tools are appropriate. So these are the 5 equations that we're going to look at. There are actually 2 more I'm going to throw in to demonstrate some things that might throw you off if you encounter them. Small correction on the whiteboard. I believe I had a 4 plus here. This should be a 4 minus roots. We have no sign changes at all, so no positive roots, and that should have 4 negative roots. So let's begin with our first equation. And we've established that we're looking for a total of 3 roots, up to 3 rational roots. There will be 3 total roots. There's no sign change, so there's no positive roots. We're looking for 3 negative roots, and 2 of those could be an imaginary pair, a plus bi and a minus bi. So that's a possibility also. So what the rational roots theorem tells us is that if there is a rational root of this, and their roots may or may not be rational, there may be no rational roots, but if there are, the root will have a rational form. A rational number is fractional form within numerator and denominator. The numerator will have to be a factor of 60 up here, our trailing constant. The denominator needs to be a factor of the leading coefficient, which is 1. And that's often 1 when you're learning this and doing your first problems. But it doesn't need to be, and later we'll do equation number 5 has a leading coefficient. So the prime factors of 60 are 2 times 3 times 5. And of course, 1 is only 1. Using those prime factors, we can generate all of the factors, or we can just try to list them and think them up. We have 12 factors because they don't need to be prime factors, it can be any factor. And they can be plus or minus. So we actually have 24 possibilities according to the rational roots theorem. But if we stop to look at it with Descartes' rule, we know that there won't be any positive ones. We're looking for negative roots. So we just cut our possibilities in half. We just got rid of all the positive ones. And actually, even in this case, without Descartes' rule, these terms are all positive. If you put a positive x in here, there's not any way you're going to get a 0. So in this case, Descartes' rule could also just give us the same conclusion as something we see rationally. So our remainder theorem tells us that if we divide by a factor, if we divide by some x minus a, we get the remainder of that division is equal to putting a into the polynomial. And we want a root, so we don't want any remainder. So we want to divide by a factor. If we divide by x minus 2 and we get 0, that's a factor. We're also just looking for the values where the function is 0. That's what we're trying to find, where the roots, where it's equal to 0. So we'll come back to an easier way to try all of these. But we know that we're looking for the negative ones, and it makes sense in most cases to begin with the smaller numbers. You'll find that when you put the bigger numbers in here, they just don't generally work out very well. 60 cubed and 60 squared get you into some really big numbers that are not likely to work. So if you try these in order, you would find 2 and 5 and 6 negatives. So you've tried 6 numbers and found 3 roots. You can find 1 and then do division, synthetic or long division, and that makes the next step simpler if you don't mind division or you like division. But if you have a programmable calculator or a spreadsheet, you can just redo this function very easily for each possible rational root. So the roots are minus 2, minus 5, and minus 6. And that means the factors are x plus 2, because minus 2 makes this 0, x plus 5, and x plus 6. So this is the way we can write this in factored form. So we can look at this on the graph here. So let's look at Desmos for a minute, and this is the function that we just looked at. This is our function number 1, and these are the roots where it's 0. Here is minus 6, minus 5, and minus 2. So you're not really looking for this following a methodology, and not, you can always just go to Desmos and plot it, or you can go to Symbolab. But in coursework, you're going to end up in situations where that doesn't fly, and you're going to need to be able to do this on your own. Okay, so that was our first function. What I'm going to do now are 2 other functions that were not on our list here. So here's the first one. Actually, this might confuse things. Let's put blank paper in here. We've got a polynomial that orders 3. So we're looking for 3 roots. According to Descartes' rule, we have 1, 2 sign changes. So we could have 2 positive roots, or they could be imaginary pair. And we could have 1 negative root. So we're going to try these out, and according to the rational roots theorem, in this case, we only have, it's very easy, we only have plus and minus 1, factors of 1, and the plus factors of 1 and the leading 1. So we put those in using the remainder theorem, and we get that f of 1 is plus 1, f of minus 1 is minus 1. So we don't have any rational roots in this case. We're going to have 3 roots of some kind, but they're not rational, and they may or may not be real. So one easy thing to look at in any function is put in 0. Okay, the value is obviously 1 at 0, and we determined it's minus 1 at negative 1. So it must go from positive to negative and cross 0 somewhere in here. And there is a theorem for that with all the appropriate terms and conditions, and that's a different topic. But logic would tell you that there's probably a root between -1 and 0 because it went from negative to positive. So let's look at that one on Desmos here. Okay, let's get rid of our first one, and let's go down here. And I have this one set up as a slider so we can change this constant. But right now, C here is a 1. And at -1, we had -1. And at 0, we had +1. And sure enough, in between, it crosses the axis. So there's a real root here, but it's not rational. So this is an irrational root. And it's not a simple square root. It's we don't know what it is. I'm not going to make any effort to find that. There are no other real zeros, so the other two will be complex. I set this up to change the constant, so let's try changing that to, if we use 2 instead of 1, we do have a rational 0. So let's look at that one. Okay, so if I do this, I'll find out that -1 is a factor. And that's what we saw on the graph a minute ago. I can find that using my rational roots theorem. My rational root possibilities are plus and minus 1 and plus and minus 2. So I found that factor. I don't know what's left. I don't know anything about the other two, so let's just do the long division in this case. And if you divide this, you'll find that you can write this in factored form as x plus 1 times a quadratic that you cannot factor anymore in real numbers. If you studied imaginary numbers, the roots of this are 1 plus or minus I. And remember, we said at the beginning that when there are imaginary roots, they come in pairs. There has to be a plus I and there has to be a minus I. So that's why up here, if we don't have 2 plus roots, then we have to have 2 imaginary roots. We can't have 1 imaginary root unless your coefficients are imaginary, which we'll almost never deal with. Okay, so that's our second function. I just wanted to illustrate what happens here in a case where you have irrational root or an imaginary root so that you don't come across that and wonder what the hell's going on. Let's look at one more function here to introduce how we can make use of Excel. So this one was not on our list either, but we can use our methodology. We have order of the polynomials 3s, and we have 1, 2 sign changes. So we're looking for 2 positive roots, so 2 imaginary pair, and 1 negative root. And total of 3 roots. Trailing coefficient is 6, and as usual so far, we have a 1 in the leading position. So our factors are 1, 2, 3, and 6. And they could be plus or they could be minus, and I can try these all out using a calculator or whatever. What I'm going to do in order to try these out easily, and this will become more powerful momentarily when we have a larger list, like we already did in our first function. Let's go to Excel. So what I'm doing in Excel is basically generating these factors. So in this column here, here's my 1, 3, 2, and 6. And this is where the prime factors come in. So the prime factors of that 6 are 2 and 3. And over here, I alternate the 3 with a 1 and 3, 1. And here, I alternate every 2 steps. And then I just multiply all those possibilities and I get my factors. This is a lot like building a truth table in binary work. So 0, 0, that gives me 0. If I want 1, I have a 1 and I have no 2s. Next I have a 2, no 1s, so that's my number 2 in binary. And here I would have a 2 and a 1 and I would have a 3. So if you've done anything with truth tables and logic, this is literally the same thing you can use to generate this. And what you're doing is just generating a list of factors. And now that you have a list of factors, you can just calculate the value of the polynomial for each one of them. So this equation up here is just my polynomial. And then I have to do this for the negative values also. So this is just equal to the negative of this. And then I calculate the function for that. So I've very easily calculated all 8 possibilities in a simple spreadsheet. And I found that I got a 0 for 2. Back here, so I know that f of 2 is 0. And spreadsheet is a powerful tool for doing that. But if you don't want to use a spreadsheet or you're not familiar with them, you can actually just use a calculator or whatever and try these out. Okay. If you're not familiar with spreadsheets, you should get familiar with them because it's a very powerful tool for many things. So we found one positive root. So if we have one positive root, we have to have another one, because if it's imaginary, it would come in a pair, and we don't have a pair anymore. We have one plus left, and we have one minus. So this means that we're going to have an irrational pair. It's not imaginary, but we didn't turn up as a rational root either. So again, we'll go into dividing this. You can take your original polynomial, you divide it by the factor you know, x minus 2, and you get x squared minus 3. So in factored form, you can write this as x minus 2 times x squared minus 3. And this gives you 2 roots of plus or minus 3. So just like this has to be up here, and a plus bi has to also have an a minus bi. Down here, anytime you have an a plus the square root of something, you also will have an a minus square root of something. And if you know the quadratic formula, you can see where this probably comes from, because you might encounter a case like that sometimes too. So let's go back to our originally planned functions here, and these will go a lot quicker because we're going to do these on the spreadsheet now. So the first one we already did, but let's go back and look at it on the spreadsheet. We'll go to Excel. There we go. And here's my original starting function. So this is the same thing. I have 4 roots. Remember, when we started, we found that the prime factors of the 60, the 60 is a trailing coefficient, constant. That's 2 times 2 times 3 times 5. So I list those. I alternate this every 1 block. I alternate this every 2 cells. I alternate this every 4 cells. And I have to alternate this every 8 cells. So I have 8 2s and then 8 1s. Some of these are duplicates, and I've graded those out. So this is a 30, and I have a 30, yeah. This 30 is using a factor of 2 here, and this 30 is using a factor of 2 here. Because I have 2 prime factors of 2, I'm going to have some duplicates here. And that doesn't really matter. In the end, I decided to grade those out. And then I did the same thing. You just multiply each combination of prime factors, and you get each factor. And these are my factors. Should be 12. 1, 2, 3, 4, 5, 6, 7, 8, and 11, 12. Those are the 12 factors that we had listed earlier. And then we need the negative factors. And we just evaluate the function. And I pointed out earlier that when you use, well, we know there are no positive ones, but even negative ones, if you start with the big numbers, you're not going to have much luck. Okay, 60 gave us some huge value for the function. 20 gave us a very large value, 30. So start with the lowest numbers. Start with the 1, the 2. You find one here right away with the 2. 3 didn't work. So start with the smaller possibilities. So we already did the first one, but this is how you would do it on the spreadsheet. So now let's look at another one. This is our second factor. Let's go back to the document here. So this is our second equation, and I'm not going to, I am still starting with my methodology here, starts with Descartes' rule and the order, so I have expecting 4 factors. One of these should be plus, and 3 may be minus, or I may have 1 plus and 1 minus, and 1 imaginary pair. My coefficient at the end now is 120. So I need to list my factors and try them out, and that's where I'm going to use Excel. Okay, so here we are in the spreadsheet for the second equation. It's at the moment minimized because just to show that it's a lot larger. We used to have 16 rows. This is what we had before, basically, same thing. Now we have 32 rows. We have the previous 4 factors, and we have a 5th prime factor. So we have to have the 16 rows with that 2, and again with the 1 without the 2. And I've grayed out all the duplicate ones. I believe we have 16 separate unique factors here in this column. So let me turn this back to 100% view here. And you can see that better, but it scrolls down quite a bit. 34 rows minus 2 headers, 32 rows of content. And it's just, other than that, it's the same as before. We have our prime factors. We had 4. Now we have a 5th one. We find the actual unique factors with duplicates, but I eliminated the non-unique ones. We find the function value, and we look for the zeros. And we have 4 of them this time. We have the 6, the minus 2, and the minus 5, which is what we had before, and I've added a 2. So I've added this factor of x minus 2. And if you go to the function, you can see that up here. I just added the factor. I didn't retype the whole function. So one note on Descartes' rule, it may seem like we're not paying much attention to that here because we're just using the brute force test every factor method. And that's true if we're doing the Excel method. If you were not using the Excel method, you would be testing these factors manually and calculating them out. And we knew when we started that we have as many as 3 negative factors, and we had for sure only 1 positive factor. The Descartes rule would indicate to us that we should start with the negative factors because we have a higher chance of hitting a root that way. So I would have started with minus 1, minus 2, and minus 2 I would have found 1. It's possible that 2 are imaginary, in which case it would be a toss-up, but given what we know, we have a better chance starting with the negative ones. So that's the second one. That's a lot like the first one, except that instead of 16 rows, which was 2 to the 4th, now I have 2 to the 5th rows, or 32. Let's take a quick look at this on Desmos. So this is what the function looks like. And here are our roots, minus 6, minus 5, minus 2, and plus 2. So that's the second one. So I found all of the factors. This time I had 4 factors. They did all turn out to be real. And I did this by following the methodology. I'm just using Excel in order to apply the rational roots theorem and the remainder theorem because I have so many different possible roots. So now let's look at the third one. Each one of these will be a little bit different now. This again is a 4th order, so I have 4 roots. There's no sign changes, so all the roots will be negative. I could have all 4 of them could be negative. I could have a pair of imaginary roots plus 2 negatives, or they could all be imaginary. So those are my possibilities. So let's go again to Excel. And here we are in Excel for this function. And same thing, this time it's the same table, same prime factors, because once again I have 120 at the end. This time it's a plus, but the number is 120. The prime factors are the same. The table's the same. I multiply each combination of prime factors to get factors. And this time there'll be more duplicates because I have 3 factors of 2. So anything that involves a 2 will appear 3 times. Here's a factor of 2. It comes from the 3rd column. And here's a factor of 2 comes from the 2nd column. And here's a factor of 2 that comes from the 1st column. So those are just duplicates. And this time, this is interesting. I have 3 roots, but I'm looking for 4. And I have 3 negative ones, which means I need a 4th negative one. I can't have an imaginary pair. That would give me 5 roots. So let's take a look at this and see what's going on here. I have my x plus 6, and I have an x plus 5, and I have an x plus 2. Let's go back to document scanner. So I need a 4th term. So what's happening here is that one of these terms appears twice. So I'm going to need another term, and to get the 120 at the end here, I'm going to have to have 5 times 6, that's 30, times 2 is 60. I'm going to need another 2. And to get x to the 4th, I'm going to need 4 x's. So this is an example of a polynomial that has a root of multiplicity 2. If you can't figure it out logically like this, you can always go back and do the division, divide out the other factors, and you'll find out you're left with an x plus 2 squared. So that's another possibility. Now we can go to the 4th equation, and this is similar. It's just different coefficients. I'm still expecting the same thing, 4 minus, or 2 minus, and 2i, or 4 imaginary. My coefficient now is 60, so I'm going to have less prime factors again. Okay, so here's the spreadsheet for this one. This is exactly like the first function. Our trailing coefficient is 60 again on the polynomial. So we have the same factors, and we just look for the zeros using the remainder theorem. And we find minus 6 and minus 5. So we found 2 rational roots, and we're looking for 4. And we're going to see in this one that 2 of them are complex. You can see on Desmos here there are 2 real roots, which we just found, minus 6 and minus 5. So let's go back to the document camera and have a look at what's going on with this one. So I have x plus 6 and an x plus 5. And I'm going to assume here that that this is an imaginary pair. To be sure, you could divide this out, or you can take a good guess here as well. If it's an imaginary pair, I'm going to have an x squared here, and I'm going to have an x to the 4th, which I need. And I have 6 times 5 is 30, but I need 60, so let's try a plus 2. So this means that x squared has to equal minus 2, and x has to be plus or minus square root of 2i. So this one, I found the 2 rational roots using my methodology. There were 2 left. So our last function here involves a leading coefficient. So in the leading coefficient, my possible roots are going to be factors of 30 over the factors of 6. And so Let's take a look at how to do that on the spreadsheet. Okay, so here we are in Excel. This set here, this part of the table is just like I would make, like I made before. I alternate the 5s, and then the 3s every 2 cells, and the 4s every 4 cells, and I calculate the function. But I have a leading coefficients, and now in the denominator, in addition to 1, I have to have each of these factors divided by 2. And here are those factors. So this is the 30 divided by the 2. And these are the possibilities with 2, which is a factor of 6 in the denominator. I also have to divide by 3, and I have to divide by 6. So I have my factors of 30 from the trailing coefficient, which is the numerator, and then I have to have 4 different possibilities of denominator. After that, it's just like before. I calculate the function. Here's the function. The leading coefficient is 6. Trailing coefficient is 30. And I find my zeros. I have 2.5 appeared twice, so that's a duplicate. So I have 2.5, and I have minus 0.67. So I have 5 halves, and I have minus 2 thirds. So let's go back to the document scanner. And I'm actually looking here for 4 roots. Turns out that 2 of them are imaginary. The 2 I have are x minus 5 halves times x plus 2 thirds times something is equal to 0. I can rewrite this as, let's see, this could be 2x minus 5. This is 3x plus 2. And this has to be times something, and this will equal my polynomial. Here's my root of 5 halves. Here's my root of minus 2 thirds. I can fill this in. I have a 2 times a 3. That's a 6. So I'm going to need a 1x squared. To get 30, I'm going to need 3. I'm going to have a plus 3. This will give me a minus 30 that I needed up here. Okay, so that was our last function, and we finished looking at a variety of functions, and we've applied our methodology to each one. Don't be fooled by the use of Excel. It's perhaps a little bit of a shortcut. I'd rather think of it as a tool. To use the irrational roots theorem, we need to know what all the factors are, and Excel gives us an easy way to do that. We need to try each factor, and that's easier to do on Excel. We could do that all by hand. It would just be a lot more tedious. So what I'm using here is a tool. It still requires me to understand what I'm doing and to understand the problem. It's not the same as going to something like Desmos, and we didn't look at any more of them on here, did we? But maybe I'll think about making these Desmos and Excel spreadsheets available on my website, jamesfrankenfield.com. I need to start putting some of this educational stuff on there. I have things that are written that are not videoed. So I may make those available. You can go to Desmos, you can go to Symbolab, and you can do that so much that you don't understand what you're doing, and I promise you that I'll catch up with you if you're continuing in math. Certainly if you're in a STEM field, that will catch up with you. Somebody's going to expect you to be able to explain how you found your roots, or to do it without those tools. So there we go, and a lot of times, if you're just being introduced to this, you have simple problems, you don't need the Excel. We started out doing some that didn't require that at all. But what I'm just not seeing is the combination of tools. People are just scrambling to find one root, doing a bunch of division, and they kind of scramble to find another root. People answering on Facebook are not explaining any of this or what they're doing. And the other thing to comment about is that you should be doing problems like this on your own. One thing people use tutors for that's really not productive is they ask the tutor to just walk them through the homework problems and explain it. And it makes a lot of sense. You know, I can explain physics homework to a university student and they think it looks easy and they're, oh yeah, I see that, that's no problem. Well, they haven't done it themselves, and then they go in and they take the test and they can't do it themselves. And you know, usually with university students, they drop the course and just disappear. And I guess eventually they'll take it again. Sooner or later, they have to pass it. But you need to be able to do this on your own. And I hope this video will help explain the tools and the methodology so that you can do a few practice problems, starting with some simple ones. And then you can understand what you're doing. So you can do this on the exam or as part of a longer, harder problem. Okay, let's go to the wrap. Okay, let's wrap up what we did. We talked about factoring polynomials here, and we have some tools we can use. Most of the time we don't go into the brute force in Excel, but we can do this using these tools is much simpler. We don't have to do a lot of division. We don't have to do much guessing. We started with this one, which was our basic equation. And we looked at some variations, and we did that using Excel. Excel's kind of the brute force method. You can generate every positive and negative factor of this constant term. You don't need to do that on a lot. In fact, you don't need to do it at all, but it is a powerful way to quickly and easily do that. The important thing is that we have these tools that can help us reduce the things. Okay, we know from the order how many roots we're looking for. Descartes' rule is often overlooked, but in our first problem here, it reduced the number of factors to try by half. Okay, this one had one sign change, so we had one positive factor. We know what we're looking for, and this is often overlooked and underestimated how useful this is. The rational roots theorem is something people do use. They just jump right into trying random factors of this trailing constant without eliminating any. And then what they do when they try them is they just start doing lots of division, which you don't need to do because if you plug in the potential factor, okay, 60, a factor of 60 is 15. Let's just plug 15 in here. We get 0, it's a root. If we don't get 0, it's not a root. A lot of times you can find your first roots by trying the simplest numbers like 1 and 2 and 3, and those are not so hard to try out. Then you can divide by that if you want to, or you can continue trying other factors, especially if you have a calculator or programmable calculator. So these are the methods we can use to find the factors. Another reason I made this video is I have another one I want to do in a while with a rational function. And the numerator polynomial and the denominator polynomial are very, very large polynomials. So in order to factor those, I did use the spreadsheet method. That was the best way to do that. Short of using something like Symbolab, which just gives you the answer. So that's how you can do it. And that's how we can factor polynomials. And hopefully that will help you out. Now, every time people ask this 2 or 3 times a week, I can point them to this data. That's it. And good luck in your studies. And remember that if you need any more help or help with any other math or physics topics, feel free to contact me for tutoring. I can help you out once or twice, or I can meet regularly, whatever you need. I can do levels through calculus and some engineering courses and some things beyond calculus. And I can do easier math down to about grade 8 or so. Below that, I don't have the ability to. Okay, that's it. Bye.